we have our exam coming up in our next lesson. Kendall looks very excited. Audrey looks stoic. All right. We reviewed terms in our last lesson. For us, that was on Friday. And we sounded pretty good about everything except chapter 13. Did you go back and study chapter 13 terms over the weekend? You will tonight. Okay. All right, chapter 13 terms was the only thing that really made me worry a little bit about you. If we have time at the end of the hour, we'll run through those again. Also gave you a bunch of equations to know, and we're going to look at those equations here, some of those equations on this handout. Go and read the first problem. Actually, first of all, if you would hold up the handout so that I can see that it is completed. And Audrey did them on paper. All right, it looks like a 1 through 9 to me. All right, so go ahead and read the first problem for us, if you would, Audrey.
If a 1.6 foot diameter bicycle wheel makes one revolution every 0.162 seconds, determine 1, the angular velocity, 2, the linear velocity.
We'll stop there for now. Angular velocity. Well, velocity in general class is what over what? Going all the way back to the early part of the year. Velocity is, well, displacement over time, right? But we're talking about angular velocity, spin rate, right? So we're not talking about displacement over time, but angular displacement over time. How do we represent angular displacement, class?
Theta rad.
Theta rad, because it's an angle of rotation. Michael said radians when I asked about angular displacement. He's like, radians. Yeah, the radian measure over time. How do we represent angular velocity? It's not with a V, that would be linear velocity. How about angular velocity, class?
Omega.
Omega. So we should have started with this equation, omega equals theta rad over t. Did we use that equation? The problem is they don't give us a theta rad. What do they give us instead of radians, class?
Revolution.
Well, the 1.6 feet is a diameter. That's not necessarily that's not a amount of rotation. What do they give us about rotation?
1 revolution.
It says 1 revolution. Well, we don't use revolutions. So what do I do with the 1 revolution, class?
2 pi.
2 pi radians, right? Make it radians by converting 1 into 2 pi. The time it takes for that 1 revolution, or those 2 pi radians, it said was?
0.162.
0.162 seconds. And so when we divide, notice we're going to get per second, or if you wanted to say radians per second, you could do that as well. And what do we get for the angular velocity? Audrey?
38.785 turns 38.8.
Good, 38.78, blah, blah, blah. Round it off to 38.8 radians per second, or just per second. How many have that first answer correct? All right, Michael, questions?
I forgot. I did this one.
All right. Have it down now?
Yeah.
All right, and I'm going to write this answer down so that I have it in the future. So I made a new worksheet just for you guys. Do you feel special? All right, and then the next part of it said find the linear velocity. Well, how do I represent linear velocity, class? By the way, I'm going to put this in memory for my calculator because I've got a feeling I'm going to need it on a 3-part problem. Surely I'm going to need this later. All right, linear velocity, how do I represent it, class?
L.
Linear velocity?
V.
Right? We've been using V for a long time, linear velocity. But I said in general, how do I find linear anything if I know angular that?
Angular times radius.
Angular that times radius. Get angular times radius. Well, it gave me the diameter of the wheel, therefore we know the radius, Kendall, must be 0.8 feet. We'll plug in the memory value here, or take what's on the calculator still, in my case, and we'll multiply by the radius, which is 0.8 feet, to get what for the linear velocity, Kendall?
31.02.
I got 31.028, blah, blah, blah. All right, and but it rounds off, how many sig figs?
2.
Only 2 sig figs now, because we took the 1.6, which had 2 sig figs, so we're going to have to round this off to only 31. Remember, this is per second, and this was feet. Feet per second. There we go. Normally, meters per second is what we'd use, but we'll use feet per second because it gave us feet for our diameter, and which, of course, we got radius from. All right, questions on those first two? Of course, Michael, if you missed the first one, you were doomed to the second one. But did you, on the second answer, Michael, take whatever you had for the first and just multiply by 0.8?
Mm-hmm.
Okay, questions at all on this? The next part of the problem, read that for us, Kendall.
Suppose the cyclist pedals hard for 4.5 seconds and increases his angular velocity to 1 revolution every 0.216 seconds. Find his angular acceleration.
He actually slowed down there. No, yeah, because he was doing 0.16. Okay, so this was poorly thought through. I'll just own it instead of changing it. But yeah, if he pedals hard, he would have sped up, or he would have done a revolution in less time.
He actually had it on the lowest gear.
Oh, is that what it was? Well, we'll say that. No, really. Okay, so let's suppose he slacks off and he slows down. Since apparently I can't. So I did this late at night a couple nights ago. Yeah, bad idea to do things late at night. So anyway, I'm human too. You've seen that already a few times this year. But anyway, so he actually slows down in 4.5 seconds. My bad. This would be then his initial angular velocity, wouldn't it? Because he's going to have a new angular velocity. We're going to find it the same way. The same theta rad, which is, in this case, 2 pi radians per, and his time now is 0.216 seconds. Again, like I say, he's slowing down, not speeding up. And so what should we have found for his slower speed now, Michael?
29.08.
Yeah, so if you were working this and you're like, this doesn't make sense, he's slowing down, not speeding up, Mr. Detsky's a doofus. Well, I mean, be respectful, but I guess you're not wrong. All right, so anyway, so we can round this off to get what for his new angular velocity then, class?
29.1.
We'll round it off to 29.1 radians per second, or I'll just say per second. I'm going to put this in memory too. That wasn't an answer that I asked for necessarily, so I guess I shouldn't have necessarily started. But in fact, I guess I really didn't even have to round it off, for that matter, because it didn't ask for his final angular velocity. It asked for his acceleration. But of course, we know the acceleration, angular acceleration, represented by the Greek letter alpha, needs the final angular velocity. What was that equation for angular acceleration, class?
Make a final minus initial over time.
Good, his final minus his initial over time. Well, I have the final now in the memory 2 of the calculator. I have the initial in memory 1, so I can subtract, which, yes, will give me a negative value, because he is slowing down. It's a negative acceleration, not a positive, as I'm reminded of here. And all of that divided by the time it took to slow down this much. And how much time did it take to slow down, class? 4.5 seconds of not pedaling hard, apparently. Maybe he was going up a hill when he did this, or maybe like Michael said, it was just he shifted to a lower gear and then he, of course, had to pedal harder, but it wouldn't do as much. I don't know. It's pretty much, I'm just a failure. And so we're going to divide by the 4.5 seconds. And what should we get for his angular acceleration, Audrey?
Negative 2.5 or 1.5.
Good, and then round it off. Since we use the 4.5 seconds in this, we have to go down to only 2 sig figs.
Negative 2.2.
And we're going to have radians per second
Squared.
squared here for angular acceleration. Good news is the test actually works out properly. This is what happens when I make up new problems. I should have stuck with my old problems. But anyway. All right, negative 2.2 per second squared, and that was 31 feet per second. All right, well, you know, you lose some, you lose some. I might not use this sheet next year. All right, but video students like Gavin are stuck with this sheet, and Evan are stuck with this sheet, and possibly other students stuck with this sheet because that's what's uploaded. I ain't changing it. All right, I'll change it live, but I won't change it for the recording. All right, questions on this? You have to suffer, they have to suffer with you. All right, let's hope the rest of the problems worked out better than this. Let's go to the second problem here, Michael.
5.3 kilogram solid sphere rolls along the ground at 5 meters per second. If the sphere measures 24 centimeters across, determine its total kinetic energy.
Ooh, when you see that phrase, total kinetic energy, we need to think about this rolling sphere, and we think that as an object rolls along the ground, class, it has 2 types of kinetic energy. First of all, it has, so we might call that translational kinetic energy, but it also has rotational kinetic energy. What's that equation I'll use? There's the equation. What's that equation we'll use to find total kinetic energy, Michael?
1/2 mv squared.
Good. We'll start with the translational kinetic energy, the 1/2 mv squared, and we'll also add to it the rotational kinetic energy, the 1/2 I omega squared. The mass. Did they give us the mass, class? 5.30 kilograms, okay. Did they give us the forward velocity, the linear velocity? 5 meters per second. All right, so no problem on the translational kinetic energy. It wouldn't be a bad idea, you might recall, I said go ahead and find each of them separately and add them together. Let's go ahead and do that. That shouldn't be too bad at all. And let's try 5 squared times 5.3 divided by 2. And what is the translational? Anyone happen to write that down?
66.25.
Yeah, it comes up to 66.25, and of course kinetic energy is measured in joules. Okay, so there's 66.25 joules of translational kinetic energy. Now we come to the annoying part, the rotational kinetic energy. The 1/2 is still there, but the I. Well, for a solid sphere, what's the equation? I gave it to you in the problem. How do I find the rotational inertia, class? 2/5 mr squared. So that's going to be 2/5 times that 5.30 kilogram mass times the radius squared. What is the radius? 12 centimeters or 0.12 meters. All of that has to get multiplied together. 0.12 squared times the 5.3, divide all that by 2. And so the I value comes to 0.03816. 3816. Remember, that's kilograms per meter, or kilograms times meters squared, excuse me, kilograms times meters squared. There's the rotational inertia. But then I also have to find the omega value. Well, again, omega, class, represents angular velocity. Well, I know the linear velocity. How would I find the angular velocity? Divide by radius, right? Remember, linear equals angular times radius, so angular equals linear divided by radius. I know the linear is 5, and I know the radius is 0.12. So if I divide the 5 by the 0.12, I'll get what for the angular velocity of this solid sphere as it rolls along?
41.6.
Yeah, 41.6 repeating. That value is going to have to be squared. So I'll take that value, square it, times the 0.03816, and divide all of that by 2. And how much rotational kinetic energy do we have? I don't think I multiplied by 2/5. I multiplied by 1/2. Something, I must say, something is not right here.
I think it should be 0.03528.
Let's try another number in there. All right, 0.12 squared times 5.3 times 2/5. That's right, I did divide it by 2. I remember that now. I said, no, it's not divided by 2, it's 2/5. 0.030528. Okay, that times 41 2/3 squared, divide that by 2. Okay, here we go. How much rotational, oh, that worked out really nicely. How much rotational kinetic energy do we get? Should have come out to 26.5 joules. I was just seeing if you were paying attention. It's a Monday. All right, we add these together and we end up with how much total kinetic energy?
92.8.
92.75 joules rounded off.
92.8.
Yes, 3 sig figs everywhere, so 92.8 joules. All right, if you got this answer, you were doing better than I was doing. How many had this answer? All right, Kendall, did you feel about like I did? Questions at all on this? All right. Maybe on the third problem, we'll get our acts together here. Questions on this problem? All right. Write that down. All right, go and read the third problem for us, Audrey.
Find the heat needed to raise the temperature of a 3.7 kilogram bar of gold from 23 degrees Fahrenheit to 86 degrees Fahrenheit. The specific heat of gold is 0.126 joules times grams per degree Celsius.
All right. I was just thinking, the Bible says, let him that thinketh he standeth take heed lest he fall. Last night, a little bit of a later night with some things going on. It's like, do I really need to work this? I got this. I know how to do this. I've been doing this for over 10 years. I'm good. Yeah, it'll get you. All right. All right, so finding the heat needed. What equation do we need to calculate heat? We're obviously moved out of chapter 13 into chapter 14 math at this point. Class?
5.9.
Q equals,
Good, Q equals CSPM delta T, specific heat times mass times change in temperature. However, to Michael's point, temperature change has to be in degrees Celsius, and they didn't give us, or I didn't give you, degrees Celsius. So I'm gonna have to find what these are. First things first, 23 degrees Fahrenheit, that's no good. I've gotta find degrees Celsius. 86 degrees Fahrenheit, that's no good. You need to find what that is in degrees Celsius. What is that equation, Michael, to change from Fahrenheit to Celsius?
5/9 Fahrenheit minus 32.
Good, 5/9 the Fahrenheit minus 32. Now, Michael, your question, I believe, is, can we just subtract and find the change and then convert? No, it'll work out differently. Let's show it both ways. Let's start by just finding the temperature difference. What is this temperature difference, class?
50,
What is the change Fahrenheit?
63.
63. Let's plug in just the 63 and see what happens. So we take the 63, take minus 32, and multiply that by 5/9. And what is the temperature change Celsius if we do it that incorrect method? 17 and 2/9 degrees Celsius, temperature change. We're going to change them separately, and notice you'll get the different and the correct answer here. So we'll start by changing 23. 23 minus the 32 should give you a -9. Take 5/9 of -9, we get -5 degrees Celsius. Then take 86 minus 32 and multiply that by 5/9. And what do we get for the Celsius temperature now?
30,
And so what is the temperature change Celsius?
35.
A total of 35 degrees Celsius from the lower temperature up to the higher temperature. Do you see a vastly different answer? So you've got to change individual degrees Fahrenheit to degrees Celsius before you go finding the temperature change. Make sense? All right. The mass of the bar of gold. Very nice.
3.7 kilograms.
Thoughts, though?
0.03.
It's got to be grams because the specific heat is per gram. So we're going to change this to
3,700.
3,700 grams. And then, of course, the specific heat was given to you, 0.126 joules per gram times degrees Celsius. We'll multiply all of those things together. And how much heat is needed to raise the temperature of that bar of gold?
16,317.
And we'll round off to, is it 2 sig figs?
16,000.
16 kilojoules, or you could say 16,000 joules, or 1.6E4 joules. How many got that answer? Did we all do what Michael did? And got the crazy 17 and 2/9. All right, does it make sense now? All right, if you have time later, we may work another one of these. I'm going to read problem number 4 for us now, if you would. Kendall.
A copper rod measures 18 centimeters at room temperature, 25 degrees Celsius. Calculate the length of a rod if it were heated to 100 degrees Celsius.
All right, so if you raise the temperature of any object class, it will expand as it's heated. In this case, we have the copper rod that we are heating, and it should also expand. It tells us the original length of the rod, but we need to find the new length of the rod. What equation do we use for thermal expansion here, Kendall?
Change in length equals alpha sub L delta T.
Good. The coefficient of linear expansion times the original length times the change in temperature. What if I've given you an original area instead of an original length? Class?
2 alpha.
You use a 2 alpha, you'd be finding a change in area. If I'd given you a volume, 3 alpha, and you would find the change in volume, but it was just change in length. So we find change in length here. The alpha value, it says, is 17 E-6 per degree Celsius. The original length, 18 centimeters with some extra zeros in there. And then the temperature change, well, this time it was already in Celsius, which is awfully nice. 75 degrees Celsius. Again, this is per degree Celsius. Remember I said the sig figs are going to come from here, the unit's going to come from here. The unit actually had 5 sig figs, 18.000. So when you multiplied all of that together, what did you get for the, first of all, the change in length, Kendall?
0.02295.
But it didn't ask for the change in length. I've got one more step because it says calculate the length of the rod if it were heated. So what do I have to do with the change in length, class? added on to the original 18.000. We'll cut the sig figs off here, and we'll end up rounding our answer to 18.023 centimeters. How many had that answer for number 4? Good. All right, Audrey, question?
I just forgot to add it back.
Okay. Questions on this? All right, number 5. Michael, read that for us.
A small bar of silver, 65 grams, is heated over a burner and then lowered into a 515 gram aluminum bucket containing 400 grams of water. The bucket and water have been 1447 degrees Celsius, and the water's temperature rises to 9 degrees Celsius after the silver is placed into it. What is the temperature of the bar of silver after it was heated?
All right, and there says see page 214, and I think that's because there are some specific heats on page 214 that I don't have memorized. I don't know if you, I'm sure you don't. All right, what do we have going on here in this problem, class?
A loss of heat.
Loss of heat, gain of heat, heat exchange, right? The law of heat exchange. So this is that problem where we're going to need to say that all the heat lost, or negative heat lost on one side, is going to equal heat gained on the other side. That negative sign does make a difference. What is losing heat in this problem, Michael?
Silver.
The bar of silver. It's heated over a burner, meaning it has lots of thermal energy, but then it's dropped into the water bucket, and so it loses that heat. So the silver is going to go on the lost side. What is going to gain heat, Michael?
Aluminum bucket and water.
The aluminum bucket and the water are both going to be gaining heat in this problem. Did you have one thing on the lost side and those other two on the gained side as we worked? All right, for each one of these, though, when we find heat, class, we're again using the equation Q equals CSV_m delta T. We're going to do that over and over again. So we're going to have to plug in, of course, this has the negative, this side has the positive. So the specific heat of silver, we had to look that up, and it should have been 0.234. The mass of the little bar of silver, only 65 grams, still worth a lot of money. I'm trying to remember what silver's going rate right now. I think it's like somewhere between $20 and $30 an ounce. See, gram and ounce aren't quite the same thing. Anyway, and then the temperature change. Now, we need to remember, temperature change, class, or change of any kind, is always what minus what? Final minus initial. We know the final temperature, class.
19 degrees Celsius.
Yeah, everything right. If the water's temperature rises to 19 degrees Celsius, so does the bucket, and the silver's temperature must be dropping to 19 degrees Celsius, assuming that was the final equilibrium temperature. It didn't actually say that, but it's, I guess, more or less alluded to. So if the final temperature is 19, and what we don't know is the initial temperature of the bar of silver once it was heated, did we take the 19 minus T sub I for the temperature change? All right, got a yes?
I had it backwards.
Had it backwards. Okay, so it's gonna affect your answer a little bit then because of the way the negative sign works. Let's go to the gained side, and we shouldn't have had too many issues over here. The aluminum, we had to look up its specific heat, and it looks like it's 0.910. The mass of the aluminum was 515 grams, and the change in temperature, well, it started at 14.7, it rose to 19, class? 4.3 degrees Celsius. Plus, we have the water. We should know water specific heat. We shouldn't have to look that up. 4.18, we've used that one often enough. The mass of the water said was 400 grams, and the temperature change would have been the same as the bucket, right? Started the same, ended the same, so 4.3. We should have had no problem on the right-hand side, the gain side of the equation, am I right? All right, so let me go and get the right-hand side then. 0.91 times 515 times 4.3, 2015.195 plus 4.18 times 400 times 4.3, 7,189.6, add that to the 2015.195, and the gain side we should have ended up with 9,204.795. Should have had no issue there still. The problem came here because I've got to multiply negative 0.234 times 65 and then distribute what comes to a negative 15.21. Now the negative 15.21, when we multiply by the 19, should have come to a negative 288.99. If you had it backwards, as Audrey did, you would have had a positive 288.99. The problem is when you move it over, you would have subtracted instead of adding it on. Also, when we multiply negative times negative, we'll get a positive 15.21 t sub I. I'm guessing, Audrey, perhaps you just ignored the existence of the negative, since you're like, that doesn't make sense. And so you still had the 15.21 t sub I. So the only area it got you was moving this over. You would have got a smaller number when we should have increased the 9204.795 by 288.99 to get not something in the 8,000 range, but 9493.785. All that gets divided by the 15.21. And Kendall's like, I can't see it. Can you see over the top? Oh, you can. So hey, look at that. Look at me. All right, and divide by the 15.21. Camera can still see it. And of course, the camera's up a little higher too. It's higher than all of your heads. And so we end up getting what for the initial temperature of the silver before it was dropped into the bucket of water? 624.18, blah, blah, blah. We'll round it off to 3 sig figs, yes.
624.
Or 642.
Oh.
Oh, I'm dyslexic. It is 624 on the calculator. I just wrote 642. I'm dyslexic, you're not. That's 3 out of 5 I'm struggling on. All right, 624 degrees Celsius for our temperature. All right, did you get that?
No.
Okay, so you were on the right track until where?
I actually didn't do the 19 minus t sub I just did x, and I realized it.
Ah, okay, all right. Questions on heat exchange. Questions on heat exchange. All right. Let's go to the next one. And read just the first part of the next one for us, if you would. Audrey?
Find the frequency of a wave that has a wavelength of 0.034 centimeters and travels at a speed of 2.978 meters per second.
All right, we're obviously out of chapter 14 now and into chapter 16 with wave motion. What equation do we need to use for this problem, Audrey?
V equals lambda f.
I'm sorry?
V equals lambda f.
Good, V equals lambda f, wave speed, wavelength, frequency. And we're finding frequency though, so we're going to take our V equals lambda f and we're going to rewrite it solving for the f to get f equals
V over lambda.
V over lambda. So all we have to do is take the speed divided by the wavelength. And we should be good to go, except there's something iffy about that wavelength, class.
Centimeters.
Centimeters. I'm going to have to change it to, what is 0.034 centimeters going to need to be rewritten as? 0.00034 meters. Remember, move that decimal 2 places, and so we get a very small number of meters, very small wavelength. We'll take that wave speed, we're to go of 2.97 E8. That's like a light wave traveling through air. And we're going to divide it by 0.00034. And this seems like it might be an electromagnetic wave. What would be the frequency of this electromagnetic wave?
8.7 11.
Good. I only got 2 sig figs. So 8.7 E11 hertz. There we go. 8.7 E11 hertz. Did we get that? All right. There was one year my kids in my class could not remember hertz for frequency, when to measure frequency. It's like, wham! I didn't actually hit the kid. I just pretended to hit the kid. It's like hertz. And they never forgot after that. So you do what you gotta do. Y'all remember hertz pretty well, which is good because on camera, you don't want to go hitting people. You also don't want to be messing up stuff right and left on camera either, but here we go. I done did it. My pride says, edit the video, re-record. Only these kids need to know. I'm like, no. Number 1, I'm lazy. Laziness always wins. And then number 2, it's probably good to know that teachers have unfortunate moments also. All right, so questions on the first part of number 6. Do we all get that answer? All right, going to the second part of the answer, of the problem rather. Go ahead and read that second part, Kendall.
Find the speed of a wave that has a frequency of 500 meters and a wavelength of 3.4 meters.
All right. Find the speed of a wave. They give us frequency, they give us wavelength. So I can just roll with the original problem here, right? Plug in the wavelength, plug in the frequency, just multiply. 3.4 by 540. And what do we get for the wave speed?
136.
Good. Round it off to, is it 2 sig figs again? It is.
1,800.
At 1,800 meters per second. By the way, that is approximately a speed at which sound might travel. I'm trying to flip over here. I feel like that's a number that we saw at the start of chapter 17 for one of our speeds of sound. Let's see, 1,800 meters per second. Maybe through a low density liquid or something that's in between like lead and wood. So that wasn't one of the ones listed necessarily, but it's a speed that sound could travel at, I suppose. Questions on that? Did we get 1,800 meters per second? All right. Let's move on then to number 7, Doppler effect. And who are we to? Michael again? Michael, number 7, read the first part.
A train horn emits a frequency of 375 hertz. If a train approaches the railroad crossing at 14.5 meters per second, what frequency does the person standing at the crossing hear as the train approaches?
All right. Person standing at the crossing. So the person's velocity is 0. All right. The train horn emits a frequency of 375 hertz, class. That is the F sub s, right? That's the frequency of the source. We're finding the frequency the person hears. We're finding the frequency the person hears. F sub o, right? We're finding F sub o. So in other words, we're solving it the way we usually do, right? No weirdness going on here. And the V sub o, of course, is 0, so we can kind of ignore that. It is important to get the correct V sub air. It says the outdoor temperature is 59 degrees Fahrenheit. What do I need to do with that, class? Change it to Celsius before plugging it into the equation. V sub air equals, let's not forget the 331.5 times the T sub C plus 273 over 273. So we need to figure out the T sub C first. Remember, subtract 32. Where are we? 59 minus 32, 27? Take 5 9, that'd be 15? 15 degrees Celsius? So we'll plug in 15 degrees Celsius here. And don't forget to take the square root times 331.5. What is the V sub air going to be? 340.48, blah, blah, blah. I'm tempted to just put this in memory. And that's probably the easiest way to go. So we can say that the observed frequency is the frequency of the source, which it said was 375 hertz, times the memory value in the top, again, technically plus or minus 0, because the person isn't moving, the observer's not moving, all over M1 minus, and the source is moving, it's approaching. So I will say minus what?
14.5.
A positive 14.5, or just minus 14.5. So we'll take the store 1. Take the memory divided by the quantity, recall 1 minus 14.5, close parentheses, and then multiply that by 375. What frequency is heard by the observer who is just standing there, class?
392.
At 391.68, blah, blah, blah. It is 3 sig figs, I believe. Yes. So we'll say 392 hertz is what is heard. Did we get that for the first part? Second part of the problem, though, says after the train passes. Well, after the train passes, what happens to its velocity? It becomes negative, but we get minus negative, which gives us positive. So when we rework it, recall 1 divided by the quantity, recall 1 plus 14.5, and multiply by 375, what frequency does the person hear now?
360.
We have 359.68 at a dot, or rounded off 360 point hertz to keep the 3 sig figs. All right, you get 360 point hertz for the second one. And the third part, if you chase the train, it says a person, and now it's you. I guess you are the person. There's this obvious shift in person that Mrs. Henderson would be very displeased by. If the person, potentially you, chase after the train at 6.30 meters per second. By the way, are you going to catch the train if you're chasing after it at 6.30 meters per second? No, because it's traveling 14.5. But if you decide to chase the train, so choo-choo train goes this way, you are chasing after train. Your velocity now is positive, because you're chasing after the train, you're going toward it. Now you're not catching it, but you're going toward it. So we're going to have a positive 6.30 here. The train is still going away, so the train is still negative, but it's the minus negative, so that still gives us a positive. So now we'll take recall 1 plus 6.3 divided by the quantity recall 1 plus 14.5, multiply that by 375. And what frequency do you hear in the third instance of this problem, class?
366.
Good, 366.33, blah, 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 but rounded off 366 hertz. A slightly higher frequency if you run after the train versus what you'd hear if you just stood still. Do we get that for the final part? All right, so no problems on Doppler effect, I assume. All right, got 3 different answers there. All right, let's take a look at number 8, and we're to Audrey.
The train horn from earlier sounds 115 decibels to a person standing 1.50 meters away from it at the railroad crossing. How loud does it sound to a person sitting 5 cars back and is convertible 22 meters from the crossing?
All right, now this is a question of loudness at different distances. Do we have an equation that relates loudness at different distances? No. We have an equation that relates what with different distances, class? Intensity. So we have to first convert
To loudness, intensity.
They give us loudness. We have to convert to intensity to find a new intensity. And once we have the new intensity, we have to convert that back into loudness again. All right, so it's one of those 3-part problems. All right, so first things first, we can't use the 115 decibels. So we're going to take 115 decibels and convert that into intensity. What's the equation we use to relate loudness and intensity? Kendall?
Is the beta equals 10 times loud over I, or something?
Class helper. Good, I over the I sub naught. 10 times the log of I over I sub naught, the relative intensity here. All right, so we need to start by taking the 115 decibels. That goes right in here for the beta. Then to get the I by itself, class, 3 things. And what is I sub naught? 1 e negative 12. So we're going to take the 115 divided by 10 anti-log times 1 e negative 12. And what do we get for the intensity that the person at the crossing has to deal with? I'm going to put that in memory. 0.3162 blah, blah, blah watts per meter squared. That's almost the threshold of pain, right? 1 full watt per meter squared would be threshold of pain. This is really close to 1. Okay, so it's almost painful to stand right next to the railroad crossing as the train goes by. It's more painful if you're actually on the tracks as the train goes by, but we're not on the tracks in this problem. All right, questions on this? Yes, sir.
Well, I can have a question. I was just.
Oh, you're just, okay. So I thought that was a way of raising your hand in such a way as to get attention. All right, so we get this initial answer. Now that we know the intensity, again, this is the first intensity that is given. This is the intensity at that first given distance. So now we go to what equation, Michael?
I1 R1 squared equals I2 R2 squared.
All right, so we take that first intensity that's now the memory value, the 0.3162. That's at the distance of 1.5 meters from the railroad tracks. That is way too close for comfort. Can't even imagine letting my kids stand that close to the tracks as the train goes by. All right, 1.50 meters, we're going to square that value. We're going to find the intensity for the guy who's sitting in his convertible, and he's how far back? 22 meters back, and we're going to square that value. So memory times the 1.5 squared divided by the 22 squared, and what intensity does guy in convertible have to deal with? Do we happen to jot that down?
0.00146.
All right, 0.00146, blah, 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 watts per meter squared. Then we're going to put that in memory too. Now, the question asks that what intensity does guy in convertible have to do with this? Says how loud. So now what do I have to do, class?
Convert back.
Back to loudness. This time I know the intensity and I'm finding the loudness. So what do I do with the intensity that's on my calculator and or in memory too?
Divide by I sub naught.
Which is 1 e negative 12.
Take the log.
And then
Multiply by 10.
times 10. And what loudness does guy in convertible hear?
91.7 decibels.
The 91.67 rounded off, it is 3 sig figs again. 91.7 decibels. Did we get this answer? All right, good. This is something I know has been giving some of us some trouble before, so wanted to make sure we had that nailed down. In fact, I wanted to make sure it was nailed down so much, I made a second problem to give us some practice with this. And to go and read that final problem, if you would. I think we're back to Audrey.
A passenger jet creates a roar of 120 decibels at a distance of 15 meters. Determine how loud it would sound at a distance of 2,750 meters.
All right, I got a feeling it's more than 120 decibels if you were only 15 meters away, but we'll play along. We have no ill will against the guy who writes these problems. And anyway, so we start off with 120 decibels. Well, again, we can't use 120 decibels class. We have to change that to intensity. So we divide by, take the anti-log, multiply by, and what do we get for the first intensity? Do we happen to jot it down?
One.
Comes evenly to 1 watt per meter squared. So it's just causing pain. That's what goes in here. In fact, we don't really even need memory for that. A number as easy as 1 watt per square meter. So ditch the memory on that. That was at a distance, it said, of 15 meters. It wanted to know how intense it would sound at a much greater distance as it flew overhead about 1 mile and almost 1 3/4 miles up in the sky at
2,750.
good, much higher in the sky. It shouldn't sound nearly as loud if it's that high up. So we plug it in, right? And we divide. We don't forget to square. And what do we get for the intensity higher up? Small little decimal. Anyone happen to have that?
0.0000297.
I got 4 zeros. 0.0000297 blah blah blah. That goes back in here now, and we change that to loudness, divide by the 1e negative 12, take the log, multiply by 10, and how loud does it sound once it's up high in the sky? What do you get for our final answer?
74.7.
74.7, it is 3 sig figs again, so yes, 74.7, 3 rounded, 74.7 decibels. Did we get that answer on the second one? All right, so we definitely, if we got both of those, we should be really good with that process. Again, that was one of the only things that gave us trouble on the last test, so I want to make sure we're good on that. Questions on anything else on here besides why wasn't I better prepared, and that is my failure on my part, and I apologize. Hopefully you're able to still benefit anyway. Questions on these problems. Are there any problems on here you say, we've got 5 minutes left or 6 minutes left, could we do another one like number blank? Any of these say, could we do another one? Yes, ma'am.
Number 3.
Number 3 with the, how much heat's needed with the Fahrenheit's in it. Yeah, let's do that. So let's say, a calculator. Let's say it's about, say we have a 178 gram calculator. Let's suppose its specific heat is, oh goodness, let's say 0.531 joules per gram times degrees Celsius. I have no clue what the number really is. Calculator is primarily made of plastic, whatever plastic's specific heat is. I can Google it, but I don't want to spend the time. So we'll just make up that number and say it's right. And let's suppose we have the calculator, we leave it in our car, and this morning it was about 53 degrees Fahrenheit outside. And these numbers aren't going to be beautiful, I'm afraid. And let's suppose by the end of the day it's supposed to, well, of course you got the radiation beating down too, so the inside of that car is going to be up around probably, it's going to get up to about 82 degrees, which is hotter, by the way, than I said it was. Thought it was going to be when I scheduled the endurance run for the day. It's supposed to be like mid-70s, and I'm like, 80s? No! Happened last time too. So probably it'll be up around like 95 degrees Fahrenheit later on today. You're going to need memory values, I'm afraid. That's the downside of making it up off the top of my head, because those are not going to work out to beautiful Celsius temperatures. But how much heat is absorbed by the calculator for its temperature to rise to that level? And we're assuming the sun is not beating down on the calculator, it's beating down on the car, which warms the calculator. So radiation heats car, convection heats calculator. Well, one of them worked out okay. And I just rolled with the fractions into the calculator, decided to spit out decimals at the end. Thought that was easier than typing in 23.333 or something like that. All right, questions here? Feel better about that now? All right, anything else? We still have about 3 minutes. Any other problems? Say, can we do another one like this one? Like after the way that one worked out, no. Questions? All right, let's tell you what, let's hit some chapter 13 terms again very quickly. Again, what do we call spinning motion, class?
Rotary.
Rotary motion. Orbiting motion would be called circular motion. Together they're angular motion, right? But rotary motion, that's spinning motion. Spin rate, how fast an object is spinning. Angular velocity. Change in spin rate. Something starts spinning faster or slower. Angular acceleration. Amount of rotation is called angular displacement, right? Measured in radians, represented by theta rad. Resistance to change in rotary motion. Rotational inertia. Rotational inertia depends on two things. Mass and distribution of the mass. In general, I, rotational inertia, equals mr squared, right? Where there's some fractions depending on the whatever. The product of force applied perpendicular to a radius and the radius of that force. Torque. Again, torque is what causes rotation. Torque causes angular acceleration. What's the law of torque?
T equals F.
Well, tau equals Fr is the definition of torque. The law of torque is the other equation. Tau equals
Something alpha.
I alpha. Tau equals I alpha. Two directions of torque. Clockwise and counterclockwise. And if the sum of the clockwise torques equals the sum of the counterclockwise torques, we have
Equilibrium.
rotational equilibrium. There we go. All right, those are the main things to know from chapter 13 off the top of my head. All right, exam tomorrow. Study diligently and be prepared for that. And that'll be 3/4 of the physics class in the books. Have a great rest of your day.